good morning. Thank you so much for coming to the ITC Colloquium. And it is my pleasure today to introduce Robyn Sanderson, who is an assistant professor of physics and astronomy at the University of Pennsylvania and a leading expert in galactic dynamics and dark matter. She completed her PhD at MIT in 2011, spent 3 years of postdoc at Kapton Institute in the Netherlands, and then held an NSF fellowship at Columbia, NYU, and Caltech before joining UPenn. Today, she will be telling us about how the Milky Way is far more dynamic and complex than once thought, and how we can use the Milky Way as a springboard to understand other galaxies in our cosmic neighborhood. So, thank you. Take it away.
Thank you. Excuse me. Thank you guys so much for having me. So today I'm going to tell you a little bit about a story that's been growing for a while. So I don't need to remind you all what dark matter is, but I'm going to do it anyway, just to get us into it on this morning. So this makes up 30% of the total energy density in the universe, 90% of all the matter that makes gravity. We don't know what it is. So for a long time, there's just been this convergence of questions in astrophysics and particle physics. On one hand, astrophysics indicates that gravity is, like there's stuff out there that's gravitating that's not visible. And on the particle side, there are some holes in the theory. We can't uniquely predict all the properties, even of the particles we know about, just based on our current theories. So it's been tempting for a long time to ask whether these problems have the same solution. But to situate this a little bit, if you're a particle physicist, then you're interested in the microphysical interactions of one of this big forest of dark matter theories. While if you're an astrophysicist, you are looking at length scales that are so much larger that you're essentially limited to an effective theory that represents maybe a whole class of the theories that a particle physicist would differentiate between. So generally what people do when they're making astrophysical predictions for dark matter models is that they have some cross-section for interactions between the dark matter and other stuff, and some primordial density that this stuff takes. And that's pretty much it. Lately, people have started to put in little variations to this, like screening scales, decay, things like that, but that's really the exception rather than the rule. And the reason I bring this up is because despite this enormous level of abstraction, most of our strongest constraints on dark matter are still astrophysical. And so I think it's really worthwhile to continue along this line because we've been able to do so much with it, even though we're working at so much of an abstracted scale compared to the underlying theories. All right, so part of the reason for that is that if you use astrophysical constraints, you have a long time for dark matter to make itself known, right? So this is the beginning of the universe, and now all this stuff you probably know about, right? If you're doing astrophysical tests that are sensitive to microphysical theories, you're probably working in this little region of the universe back here. But for an effective theory, you have this whole timeline to play with, right? So for instance, our galaxy contains epochs or information from all of these different epochs because it started forming back here, and it's accumulated other smaller galaxies along the way. Likewise, you can probe a range of scales just by considering a single galaxy. So this is an example of the power spectrum, the amount of structure at different scales that you get in different theories of dark matter. I should add a line to this that goes up like that, because now some theories are predicting there's actually more structure than cold dark matter at small scales. But if you vary the theory, again in this sort of abstracted sense, you get different predictions just around the scales that you might expect to be able to measure with the Milky Way. And so this is the range that we call near-field cosmology. And what that means is that if we could just see the dark matter, we would have solved this problem already, right? So we could just go out, we map the dark matter, and we say, okay, well, is it this, or is it that, or is it that? So that's easier said than done, of course. These are three theories that we've used to make predictions for Milky Way scale systems. And sometimes the differences are more subtle than others, right? There are differences between what's going on if you allow for a self-interaction. and what happens if you have no self-interaction. And there's definitely differences if you have a small component of the dark matter that's allowed to cool like hydrogen does. But again, we're still looking at what these actually do to the histories of the galaxies that form in these kind of halos. And since we can't look at the dark matter directly, we have to find indirect ways to see it. Oh, because this is zoomed in by like a factor of 10. So they exist, but they're outside this region. The other thing about this is that I'm only showing the fraction of the dark matter in this system that's atomic, that can cool. About 95% of it is CDM, and so that makes this distribution plus a bump in the center, and then some of these little clumps that the ADM forms that are kind of like molecular clouds but don't form stars. So, all right, we have all this gorgeous data from Gaia. Let's go map the dark matter in the Milky Way. We have enough dynamical information, we should be able to do that, including all of this beautiful kinematic information on top of the map that Gaia has constructed. All right, so to first order, what you'd want to do is measure the distribution function of the stars. So that's what Gaia has done. And then you invert the Poisson-Blasov equation or the collisionless-Boltzmann equation or whatever you call this to get the global potential. And then you invert the Poisson equation to get the density, the total density of matter, which is the thing that generates gravity. And that gives you the sum of whatever dark matter you have and whatever stars you've got, right? And then you subtract off the stars, which you get from integrating your distribution function, and lo and behold, you have the dark matter distribution. Okay, so this is what people plan to do with Gaia. So let's see. In order to do that, of course, you have to make a bunch of assumptions. So people have tried to do this both in the equilibrium modeling sense that I talked about and also in the non-equilibrium modeling sense where you treat things like the tidal streams from disrupted galaxies as sets of tracer particles to map the dark matter distribution. But in order to do this, people generally assume that you have sort of a symmetric dark matter halo that's in approximate dynamical equilibrium, so it's not changing too much. The satellite galaxies that you see around the Milky Way are not perturbing that distribution too much, and they generally represent other galaxies. That the disk and the bulge have sort of been unchanged for about 10 billion years, and that their structure is not affected by the dark matter. That the tidal disruption of things creates these pretty uncomplicated cold streams that you can use conveniently to map the potential. And that if there's structure in the dark matter itself, that there's a basically isotropic field with a varying density as a function of distance of these little clumps, and you can find out where they are by looking for perturbations to your nice cold streams. All right, and then that the galaxies outside the Milky Way are basically just there because they haven't interacted with us yet, and they're not disturbed by the tides. Okay, so these are all ingredients. So how is that working out for us? Okay, so that's not the case. That doesn't really work. That isn't really what's going on. That doesn't work. That also, all those other things also don't really work. And so the reason that I put up this rather biased summary is that what we've done to test all of these assumptions is confront the mental models of galaxies that people work with to do dynamical modeling with realistic systems in a cosmological background that we can get from modern day simulations. And so all of these results come from trying to apply these models and getting slightly wrong answers. So the main reason for this is that the Milky Way is not in equilibrium like we thought. This is one of the biggest takeaways that we've found from the results of the Gaia mission. And it's not in equilibrium in ways that are both a bug and a feature when it comes to dynamical modeling. But the first question that you might want to ask is, well, why is that the case? Okay. And it's actually a fundamental prediction of our cosmological model, that hierarchical assembly connects the dark matter, the cosmology, and the formation of galaxies. Right? And to illustrate that, I'll show you a movie from one of the simulations that we used to test this. So you'll see at the beginning, stuff is emerging out of the cosmic web. But the early history of something that will eventually turn into a Milky Way-like galaxy is very complicated. And it really only calms down, in this particular case, after redshift of a half. So only at late times do you actually see something that looks like a disk in the middle and a halo in the outskirts. And this is clearly a very wide view, but that's the view that we are approaching by increments, first with Gaia and now with modern telescopes like Robyn and Robyn. And so now it looks like a galaxy, right? But up until this point, it was hard to distinguish what was happening. And so it's actually kind of beautiful that we're having these problems because it validates a key prediction of our theory of the universe, that galaxies assemble out of smaller things and emerge over time from the cosmic web. All right, so but that doesn't help us when it comes to modeling the galaxy. So what do we do now? So I'm going to argue that we can do two things. We can do better with theory, and we can make more principled comparisons between our predictions and our observations. All right, so better theory is the main part of this talk, and I'll talk a little bit about the other one at the end. This is the ITC, so. What I would argue is that we need to make predictions by using simulations that include the things that the universe actually puts into making a galaxy. So that means we need the cosmological background, and we need the coevolution of the dark matter halo and the galaxy itself over cosmic time. Part of the reason for this is that many of the things I'm going to test involve the use of tracers like tidal streams, and these have evolution timescales that are comparable to the Hubble time. So another thing is that the growth of the central galaxy in the middle of a dark matter halo changes its dark matter distribution in ways that are visible just from visually comparing these two images, right? So this is the same simulation, in one case run without a galaxy forming in the middle, and in another case run with it. And you can see that the structure of the halo to remarkably large distances is affected by the presence of the galaxy forming within it. This is a dynamical process, right? You're having a system with a fundamentally different symmetry emerging from the center of your halo, and so its imprint is obvious when you're trying to match to observations and simulations. So if you do this, it's expensive, right? You are modeling not only the dark matter and its gravity, but also the dynamics of the gas. You have to put in all these recipes for star formation, stellar winds. It's taken a lot of work by many teams to get all this right. And we're fortunate to live in an era where we can have the computational power to do this. It's expensive, but I think that the extraordinary data sets that we have merit this kind of concentration. So what I'm going to talk about today is predictions mostly for the small scale structure of these simulations, because that's the stuff that I've been working on most recently. And so that's down here at the low end. And so it pertains mostly to things we can do with the tidal streams and the satellite galaxies of something like the Milky Way. Right, so the key scales here, the satellites sort of probe the middle to smallest mass scales in the dark matter that you can get to in a galaxy scales. But the streams offer the promise of going beyond what we can probe with intact satellites, down to the level where there are significant differences between these theories for the structure of dark matter at scales too small to permit galaxy formation. So one of the biggest things that people have been doing with this, right? So the dark matter in these little intact systems can be affected by which dark matter model you have. So this is the mass of the thing and how many you expect. But you can also look for crashes between tidal streams and these little tiny things that are below the scales on this plot, pretty much. So the way that this works is that you make, in an idealized simulation of a cold, thin stream, one of these little clumps passes through, and it gives you a little perturbation in the density. Sometimes people call this a gap. Sometimes the structure is more complicated, so this is some tempting tantalizing data from a stream in the real Milky Way. And it has this, disturbances along it. And so this was a stream from a globular cluster that tidally disrupted in the Milky Way. Those are not resolved natively in our simulations. But even when you look at the tidal streams that you do see, which are from disrupted satellites, you see that there are dark matter clumps interacting with them all the time. So this is really, we really think this is happening. So it should be a valuable probe. And the reason is because it's essentially a probe of the mass scale or the mass function of these small things. So if you take one of these idealized models and you ram subhalos of different mass through it, you get different sized holes in your stream. And so by analyzing the pattern of holes that you see in real streams, you should be able to map that back to a mass function of dark matter substructure at these low masses, right? So this is one of like 2 or maybe 3 techniques that people have proposed to constrain this structure at scales that are invisible. There's strong lensing and perturbations to lensing arcs, and then there are some people that are looking at like millilensing of distant stars. But all of them struggle with the same thing, which is that subhalos like the ones we expect in CDM are really crappy at making any difference to any of these things. So this is one of only a handful of ways that we think we might accomplish this. All right. Not only that, but so far people have only done this in our galaxy. We know of a handful of streams that seem like good candidates for it. But in order to really back out the mass function, you need a statistical sample. And Robyn will provide that. So around nearby galaxies, we expect to be able to detect gaps in streams out to at least 5 megaparsecs. That gives us dozens of galaxies to work with. And it will make this a statistical technique rather than a one-off. Yes?
So you're talking about the gaps.
Yeah.
I can see it. I'm also seeing an offset, right, between one side and the other. And presumably there are also velocity signatures.
Yes.
So are you thinking of all of these, or are you just focusing on the gaps?
It depends on what information you think you can get, right? So in our galaxy, there are velocity signatures that you can go after. For something of 5 megaparsecs, that's going to be a little harder, right?
Okay.
So the first order thing is the density perturbations, because those are the easiest to observe. But I'm going to show that they're also some of the easiest to get mixed up with other stuff.
Okay.
And so that's why we need to do all of these things. But if you want a statistical sample, you have to go to enough galaxies. It's going to be hard to do it systematically across a large enough volume, unless you convince somebody to like build you your own 8-meter spectroscope or something, which could happen, you know.
One thing that needs to be, you mentioned it's a globular cluster, but if it were a satellite that was disrupted, then there would be dark matter also in the stream.
Yes.
And then it complicates matters because the dark matter in the stream can the self-gravity can prevent disruption.
Yes. So I love this because nobody ever talks about it. So the focus so far has been on the signals that you get from globular cluster streams because they are the kinematically coldest, right? And we also don't think that they came in with like a whole bunch of other like dark matter structure because they're globular clusters, right? So first of all, I don't think that assumption is entirely correct because I think most of the streams that end up on orbits or most of the globular clusters that end up on orbits that make these kinds of streams, a lot of them come in as part of another galaxy, right? Because they have to be on an orbit that's recently eccentric enough to bring the thing into a place where the tides can break it up. And you don't get that very much with stuff that formed in the Milky Way itself. Okay. The other thing is, I think that it's led people to underestimate the usefulness of streams from satellites because then the satellite has all these little companion halos that are going to hang around it as it tidally disrupts and bounce along in similar orbits and amplify that signal. That's part of what you saw happening in this movie, right? Because clearly some of those things are stuff that fell in as subhalos of this guy, and then of course they stream out similarly to the stars. That's I could give a whole other talk on that. Oh my God. Okay, but we're going to focus on globular cluster streams today. All right. So, how well does this work really? Okay, so I already went over there are two things that you have to do in order to figure out what the expected signal from this process should be for globular cluster streams, right? So the first is you have to model the Milky Way so you know how efficient it is at disrupting stuff. So typically what people do is they break this up into a bunch of parameterized models that correspond to different structures with different symmetry within and then they usually keep this time independent just because you don't have a good prescription for that a priori. So altogether, this gives you about 15 or 30 free parameters to model the potential in which these disruptions are happening. One of the problems with that is that we know that our galaxy is experiencing big changes to its potential that are not equilibrium. It's clearly time dependent. And one of the effects of this is that the incoming clouds are dragging the population of subhalos around and concentrating some in regions and pulling some away from other regions. And so what this map is showing is sort of a hybrid of some of our simulated stuff. So we have a system among our cosmological simulations that has an interaction with a thing like an LMC. It's on a fairly similar orbit. And so what we did was we forecast where you would get increases in subhalos relative to the trajectory of the LMC. And you get some that are that came in with the LMC and are sort of in a leading tail. There are some that are concentrated because the Milky Way is in a two-body system. And then there are some that are scattered along its past trajectory. And so on one hand, this could be a feature because you could say, oh, well, I want to go look for streams like these guys that are close to the places where the subhalos are concentrated because then I'll have a larger chance of finding one. But if you don't assume that the distribution is not in equilibrium, then you'll misinterpret the frequency of those interactions and come up with a wrong density for your dark matter subhalos. Right? So we have to take this into account. The other thing people do is they have to construct a model for the stream, right? So you put your stream in a static host galaxy with one of these analytic models. If you want to see what happens when subhalos hit it, you put them in usually by hand. Sometimes you just send one on a trajectory to make the gap that you think you see in your data. And for the stream, what people generally do is they assume some rate at which things are leaving the progenitor, and then just release those particles at the Lagrange points of some mass that's modeling the progenitor, right? So some of these models include the gravity field of the progenitor. This one does because you can see how there's some structure right next to the progenitor. Those are things that are like just taking a long time to leave, and they oscillate back and forth on little epicycles and make gaps that have nothing to do with dark matter. That's been known for a while. But most of the time, people don't model the progenitor itself because that's very computationally expensive, right? If it's a globular cluster, that's a collisional system. You have to model the individual stars so that you get mass segregation right, all of that. It's expensive, so people do this because then you can easily explore parameter space to fit your observed data. All right, so I think we can do better than this now, so we set out to try to do a little better, at least to make the predictions that should give us a baseline for the kind of structure that we should see exclusive of subhalos in streams in our galaxy. All right, so the parameterized modeling, like we said, it ignores a lot. Here's a video of like the last half of the life of the Milky Way-like object. The LMC is not necessarily even the only thing we have to worry about. So how could we do better at modeling the galaxy and fold in some of this stuff? And what we decided to try was to use an old thing that you probably learned about in E&M a million years ago, and represent the potential with basis function expansions that solve the Poisson equation. And so this gives us a compact representation of the system that is flexible enough to get these shifts in the local distribution correct, but which we can use to control the amount of substructure just by taking truncating the basis expansion at a different L. And so for the round part of the galaxy, we use a spline instead of Legendre polynomials for the radial basis. It gives us a little more flexibility. And then a spherical harmonic expansion for the azimuthal variations. And then for the disk, which is very different symmetry, it's very flat. You don't want to make your spherical harmonics work that hard, so you use splines in both R and Z for the basis functions, and then a Fourier series for the azimuthal system. And what we've found is that this combination works really well to represent the cosmological galaxies that we have in our simulation suite.
And these are all time dependent?
Yes. So what we do is we take this and we fit it to every single snapshot, and then you don't any longer have to worry about all this stuff. But you still have an analytic model, which is really nice because it's fast. You can take this thing and then just interpolate the forces that you get from the BFE in time, and you can reconstruct very accurately the orbits of stuff in the potential without having to resimulate your whole n-body cosmological system. All right? And we can control how much substructure just by changing the order of the expansion. And so what you end up doing is for some order L, there's some sort of characteristic angular size that you can model with the BFE. And so that'll correspond to some size of the subhalos in your simulation. And so what I did here was I took a very conservative size, which is 20 times the scale radius of the subhalo. And I collected all the subhalos in one of our models over the entire time that we were modeling it with the BFE. And we chose L equals 8, which is fairly high order. And still, if you plot all the subhalos on this thing, none of them, except for a couple very massive ones, get down to where the BFE would see them. So this is an effective way to take out the subhalos from your simulation, but keep in the large-scale tidal sloshing of the potential to see whether that makes a difference to what happens to your streams. All right. It also lets us tune whether we put the substructures in or not without having to do it by hand, right? Because I can just I can either read the halo catalog and put them all in as they would come in the cosmological system, or I can just turn them all off by using the BFE. And so I don't have to do that one by one anymore, but I still have control over it. All right? And when you do this, you do a really good job of reconstructing things out of your simulation. So on the top is this tidal stream from one of those disrupted satellites in the full simulation. On the bottom is the same thing, but using the BFE reconstruction of the potential with a linear interpolation in time. The one key to this working well is, one key to it is that you get the time dependence in there, because if not, you lose the ability to reconstruct the orbits after a gig-year or two. The other is that we interpolate the forces rather than the coefficients of the BFE, so the forces stay physical the whole time. And you can look at the residual forces relative to the accelerations felt by the actual particles in the simulation, and if you zoom in on the disk, you can see the spiral arms that we're ignoring. All right. So one of the coolest things you can do with this is reinsert stuff that was too small for the cosmological simulation to resolve. And we were lucky that initially people had started to get curious about where in these simulations globular clusters would get formed. And so in a paper a couple years ago, Mike Grudich went and looked for places where you have like a high density of gas in the simulation at early times and tagged all of them as likely sites for globular cluster formation. So we have a self-consistent, at least within our cosmological model, location for where all the globular clusters that might end up in the Milky Way today are born. And then Carl Rodriguez hooked this up to his Monte Carlo models of the internal dynamics of globular clusters. So these do all that stuff that I talked about, where you have to, get the mass segregation and the binary population right and all of this stuff, but does it in a faster way with Monte Carlo using a code called CMC. And in order to couple these two together, they followed the globular cluster tracer particles through the simulation and recorded the tidal tensor that they were feeling at every point. And that gives you an idea of how this thing is losing mass as it goes through the galaxy. All right? So that keeps us from having to do all this particle spray stuff because it prescribes for us when the thing is losing more mass and when it's losing less mass. That's no longer a free parameter, it just comes from the model. And this is one of the things where in the models that people construct of globular cluster streams, there is the most variation. Some people assume that the mass loss rate is constant. Some of them scale it with the tidal radius. It's all over the map. So alleviating that problem is a big step forward. And we can still include the gravity field of the progenitor. We just put a little plumber sphere there so that things leak out slow enough. All right. So we now know when and where this thing loses stars, and then we put those stars into our BFE model of the same simulation. And that tells us how the globular cluster tidally disrupts and forms streams within this. And this work was mostly done by my former grad student, Anand Panatam Paisal, who's at Carnegie and Caltech now. And then our next step is going to be to make some synthetic observations of these, which is really easy given the fact that we already know exactly what stars are in the stream. So now we just have to translate their masses and ages and metallicities into luminosities and magnitudes and bands. All right? And Chitska and I and a couple other people on the team are working on that. And so we've used this system to construct the first fully self-consistent cosmological globular cluster streams. Here's two examples from our first paper. One that is nice and curly, and one that's a little bit weird looking, but also has a nice thin part. We just picked these to have orbits that were like orbits that we know of globular cluster streams on in the Milky Way. We didn't spend a lot of time because it's expensive to integrate each one of these. So we just picked a couple of likely orbits, and we got things that aren't too terribly different from what people see in the Milky Way. So they are cold. Their velocity dispersions are a few kilometers a second with some variation. Their densities are high along the stream, but then they have substructure, even though I didn't put in any subhalos. So we think that this clump is actually a result of an interaction that a merger had with a disk, and the resulting response of the disk of the galaxy ended up clumping these stars together. You can see when it happens in the simulation. And although the subhalo itself is not in the model, the response of the disk is. All right. Another thing that people use to diagnose like the shapes of halos is the alignment between the track of the stellar stream and the velocity of the progenitor. But we found that this is somewhat phase dependent. So if you look at the thing near pericenter, everything lines up. But if you look at it near apocenter, you get a mismatch between the stuff that left earlier and the stuff that's leaving now. Yes?
What relationship insert your globular?
Such a good question. So the globular clusters are there the whole time, and we have the whole history of mass loss from all of them. But what we did here was to integrate only things that left in the last 2 gigayears. So that's kind of surprising to people because there's an idea that the globular cluster streams have to be old. They are old in terms of their stellar populations, but I think they are the part that we can see as a thin stream, I think we're going to find is a lot dynamically younger than the ages of the stars. This is something that we're working on now with a statistical population to see like how long they actually last in total. But these two are just the stuff that left in the last 2 gig years. But these things have been losing mass like the whole time. And a lot of it is just all over the place now and wouldn't be readily associated with the stream at this point. That's a big reason why we want to do observations of these too, because the decision about what is in the stream is fundamentally an observational one. There's just a lot of stuff that's going to be at too low surface brightness to be called part of the stream. All right.
One other
Yeah. No, this is great.
We started off by talking about gaps.
Yeah.
And the gap is because something else goes through the stream and does something. Now here you got a clump. You said in this case it went through the disk or something?
It had a pericenter as the disk was doing this after a merger.
Okay.
And it caused.
That doesn't make a gap, but it makes a clump.
You could call this a gap.
That's
Or you
the
could
gap.
call this a clump. See, it gets a little shaggy, and when you talk to people that do the observations of these and try to do it, they're all like, yeah, this is a lot weirder than we hoped it would be. What you call this stuff is also an observational question, right? So it may be that you just like don't even connect to this part with this part once you do the observations. I don't know. Anyway, so another cautionary note that we got just from these two streams is that when you see a nice thin tail like this, you're like, oh, well, this is where the progenitor used to be. But in this particular case, it's over here in the part that's at apicenter, and the thin part is the part that's at pericenter. And so if you assume that the progenitor was here to make your stream model, you're doing something that's a bit wrong. And so our next step is to make statistical predictions. This is a teaser of a handful of streams that we've already integrated. But it's so mesmerizing that I look at it all the time. And you can see that there are lots of nice, long, thin things in here. And then there's some stuff that looks like totally not streamy. And this is part of why I say that like a key to this is going to be to do synthetic observations, because different ways of detecting streams are going to give you different answers about what's in the stream.
There are also the halo stars, right? So
Yes.
the distinction between halo stars and stream stars depends on the contrast.
Yes, exactly. And so that's the next thing I'm going to talk about. But before I do, let me just sum up. So I think we should use these kinds of simulations to set more realistic expectations for what we want to see, especially when it comes to things like how much structure do we expect in streams before we start adding the dark matter perturbations. We can efficiently capture the kind of disequilibrium that we get in real galaxies using these non-parametric models, and I think they're a really powerful tool. I haven't had time to describe the other things you can do with them, like the time series analysis of the coefficients, which is a whole great way to like look at the coupling between parts of the galaxy and how it connects to the filaments and all this other fun stuff. And using this method of what I call forced reproduction solves some of the dynamic range problems that have plagued this field for a while, and have made it possible to do this. So this will let us more reliably model the mass distribution. Although we'll have a hard time doing a full time-dependent model for the Milky Way, I do not think that the BFEs we've been using are such a high order that we can't use them to model our actual galaxy. So we've found that you can truncate the series at even L equals 4 and get a really good model. And that's not 100 times as many coefficients as we're using now for parameterized models, right? It's like 80 instead of 30. We can handle that with the amount of data we have. I believe we can. Machine learning will fix it, right? Okay, anyway. But we can also like test which of these assumptions are the most problematic by just feeding them some realistic mock data. And with these kinds of models, we can also figure out which dynamics does what, and how to distinguish between the things that are done by something else and the things that are done by dark matter substructure, which is a high value target. All right. We also found that the clouds are affecting the local density. Happily, we get some similar looking streams, so what we see when we try to do this as consistently as possible. And we find that the coldest streams can be clumpy even when dark matter halos aren't included in the evolution. Right, but I said that all of this is dependent on what you call a stream. So history's littered with times when we thought that there was a problem, but when we fixed our selection functions, the problem went away. We tried this also with tidal streams that we predicted compared to what DES found within their footprint, where they have a really well qualified selection function. So we predicted that we'd get about 8 that they could detect in the mass range that overlaps between our simulations and now these are satellite streams, not globular cluster streams. And they predicted 2, but that was before we corrected for the observational bias. So once you actually do mock observations and ask which ones you would see as a stream, then the discrepancy goes away. This is the average number before that, and this is the average number after it, and the shaded region is how many they actually found. So we do that by throwing these galaxy simulations in with models of stellar populations, an estimate for the phase space density to spread out your particles into stars to make a mock catalog, describe the survey, and then put that description onto your mock catalog to create a synthetic survey. That's a lot of work, but I think it's very necessary work. It also makes really good pictures. So one of these is the actual Milky Way, and the other one is a simulated Gaia survey of one of our simulations. And we've done this a lot now. We've done several Gaia things, and the code is a public tool, so you can go pip install it and use it on your own simulation if you feel like it. My postdoc / research scientist, Adrian, has been amazing at doing this stuff. And the reason that we're working so hard at it is because Robyn is coming. And Robyn is going to be so good for resolved star imaging of nearby galaxies. So just to underline it, this blue thing is the FAT survey, which is like hundreds of Hubble orbits. This is the footprint for Hubble for one exposure. This big white thing is one Robyn exposure. So it can do FAT in like 3 exposures. So we're looking at what you can do with this in a number of contexts. Robyn's going to do a survey of the galactic plane. We can make predictions for that. We're hoping to convince them to survey nearby galaxies, so we're making some predictions for that. And we're going to make predictions for all these globular cluster streams that we've simulated to see how many we expect to see around these nearby galaxies. We're also expanding beyond cold dark matter models to try to extend this technique to some of our other simulation suites that have the same baryonic physics, same initial conditions, different dark matter model. So I'll stop there. I think I'm probably over time, but you all ask good questions. Thank you.
Additional questions?
This is awesome, thank you.
Thanks.
Early on you showed that in fire disks settle kind of late, right, at redshift 0.5.
There's a huge range.
Yeah.
I picked one that forms kind of late to make the point, but some of them form at z of 2 and some of them get together at z of a half and everything in between.
Right, so do you know how like results sensitive to this, or whether the current or like the history of the Milky Way is more or less?
Yeah, so we have only, are you asking about specifically in the context of the globular cluster stuff? Or
Yeah, because I mean, we know that the Milky Way probably formed unusually early, right? So
yeah. Okay, so the one that we picked has a pretty quiescent history. It has a disk that forms pretty early. And I think it doesn't have a thing like the Magellanic Cloud around at present day. I think it's not quite as early forming as the Milky Way. And I think so one of the things that our globular cluster model struggles to reproduce is the very old population of globular clusters, and I think that's partly why. What we'd really like to do is use one of the simulations that we have of pairs of galaxies that look like the local group, because those form substantially earlier than the isolated ones, right? Because they're part of a bigger density perturbation, so they just get a head start from that. And I think that will help solve part of this problem. I think it's too early to say how much that matters for the globular cluster stuff. Partly, my hunch is that it won't matter so much because it seems to be that the stuff that stays coherent is not the old stuff. So if what you care about is like how globular clusters entered the galaxy or like formed there and made the scattering of stars in the inner halo, then you probably care about that. But if what you care about are the things that are cold fin streams now, I don't know that it's going to make that big a difference. It may make a difference depending on how active things have been lately in the last 2 gigayears within the simulation. But in that sense, the one that we are working with right now is calmer than the Milky Way. And like the thing that is doing the disk perturbation is like a Sagittarius-like object. So it's not that crazy to think that might be happening in the Milky Way as well. It was a long answer, but yeah.
I need the mic up. So you were talking about Robyn looking at nearby galaxies.
Yeah.
How nearby are we talking?
So I think we can probably do the globular cluster stream stuff within 5 megaparsecs, which is what the prediction was from Christian's paper that I put up there.
So not quite Virgo.
Not to Virgo, unfortunately. Although I think that in Virgo it's going to be cool to use, you'll be able to get proper motions for intact globular clusters and do some distribution function modeling with those, which is going to be fun. I just did that on the back of an envelope the other day and I was like, that's not crazy. And I didn't even talk about how LSST is probably going to find a bunch of these things in our own galaxy.
By the way, in Virgo you can see streams of
Satellites.
Of galaxies.
Yeah.
In the cluster tidal field.
Yeah.
So it's the same thing scaled up, and it might be bright enough.
Yeah. No, I haven't thought about that far away yet, but I'm getting pulled in that direction by all these people that are excited about nearby galaxies with Robyn. It's gonna be fun. And then there's all this other like cool galactic archaeology stuff you can do with the streams from satellites in the nearest like 8 megaparsecs is I think where people are saying you can really get like quality, like resolved stellar populations with Robyn down to like below the RGB, so you can really differentiate. I'm in another team that's working on what a survey of nearby galaxies Robyn would look like, and we're using this stuff. These are pictures from the mock galaxies that we're using to test survey strategies. Yes?
Thank you. Terrific talk.
Thanks.
This is more like a comment. So M31, we already know that it is full of streams that look like really, the globular clusters look like beads in a necklace. So I think that would be a very interesting object to see.
Yes.
And another group of objects that maybe you want to look at. So NGC 4258 is very far away. It's far away for this. It's about 7 megaparsecs and has a rotating system of globular clusters.
Yes.
But also the sculpture group, which is at 4 megaparsecs. There are several galaxies there that also have rotating systems of globular clusters.
Yeah.
So they are not pressure supported, and I'm very intrigued about how they form.
Absolutely. You know what's even cool is the sculpture group is in the high latitude survey field. So Robyn is already going to look at it. It overlaps with part of that field, which is going to be really cool because nobody has to even propose for those observations. You might want to go deeper than they're going for the lensing stuff, but it's very exciting.
Just last comment. In principle, gas can also appear in a stream, so then you would have 21 centimeter data that give you also velocities. Did anyone look into streams of 21 centimeter?
Yes. I don't know that work as well, but I always feel like I should. I know people have done some work on this with the clouds for sure, right? So people have been like studying the gas stream because the stellar stream is very faint and was only discovered recently. I don't know if people have worked out how to model those, just because they're a little more complicated than pure dynamics.
Because of the pressure.
Because of the gas pressure, and you have to like figure out what's happening to the stream, like because it can interact with the surrounding gas, right? So, and you have two very different like phases to deal with. I wonder though, like I feel like there's a little bit of an implicit bias in my thinking about that because all the simulations I use are Lagrangian. And so they don't put the resolution where you would see those very well. But it's definitely something that I would like to think about more because I think you're right that it's underutilized, at least I'm not paying attention to it, which might be might be the problem.
I had one question. So you mentioned that globular clusters, at least the ones you're talking about, were pretty dynamically young, like 2 to 3 years. Like, is that, like, in your experience and what you've been seeing, like, what do you think is, like, the oldest accretion event that, or maybe a typically old accretion event, like that, what kind of ranges does
It's a little too early to say, but I think they go back pretty far because we just were looking at this literally last week. We were looking at like which progenitors end up forming tidal streams. They come in pretty steadily throughout the entire like range of history.
And there's still streams.
And there are still streams, but it's not like all the stuff that ever left the cluster is still in that stream. So it's it depends on what you call the stream.
Yeah.
The other interesting thing is that they're not 100% from accreted globular clusters. Some of them are from stuff that formed in the Milky Way. One of the things we were looking at was like what proportion of the population came from outside versus inside. But we don't have the full population of clusters from that simulation integrated yet. So I don't want to make a statistical statement before we have the statistics.
Are there any final questions? Coming up against the time here. So, all right, I think we are good. Everyone, thank you again, Robyn Sanderson.